Digital computation relies on a strict architectural requirement. The system eventually forces every piece of incoming information into a definitive true or false state. When a logic gate receives complete data, this architecture works perfectly. But a structural glitch occurs when the gate receives an incomplete packet, where one input is known and the second input is missing entirely. In this scenario, standard binary architecture lacks a mechanical method to pause. It cannot hold a state open. To complete its cycle, the mathematics force the gate to guess, collapsing the missing data into 0 or 1 so the process can continue. Because hardware physically cannot represent an absolute unknown, modern computing structures, including self-configuring networks and artificial intelligence, are built on an infrastructure that automatically converts absolute ignorance into false certainty. The alternative to this premature collapse is a specific ternary logic framework built on the mathematical principle of honest ambiguity. This is distinct from probabilistic models like fuzzy logic. It doesn't rely on fractional truths or estimate a value of 0.5. It deals exclusively in structural states. The source paper suggests a fundamental link between classical logic operations, proposing that and OR gates can be expressed through a single unified ternary process. This framework introduces a third contextual parameter that determines the behavior of the gate, allowing the logic to shift its interpretation based on the system. By formalizing this contextual parameter, interpretation becomes a variable. The system gains the mathematical ability to evaluate incomplete data without immediately forcing a binary collapse. This maps the new ternary geometry. The first axiom is state 0, a firmly false, closed-down condition. The second is state 1, a firmly true, closed-up condition. The central element is state 2. This geometry represents a completely unresolved, unclosed condition. State 2 does not act as a third truth competing against 0 and 1. It is the formal mathematical symbol indicating a lack of closure. Treating an unknown as an explicit structural value, rather than throwing an error code, is the required step to build a system computing without guessing. This table illustrates a ternary AND gate handling incomplete data. The rule is 0 strictly dominates. If the gate receives a 0, it forces an output of 0. An unresolved state 2 is irrelevant. The 0 dictates reality. If we change the definitive input to a 1, leaving the second input as an unresolved 2, the logic shifts. Because state 2 could resolve into 0, dragging the output down, the system cannot logically close. The output honestly remains a 2. The ternary OR gates operates on a dual rule. The value 1 strictly dominates. An input of 1 paired with an unresolved 2 instantly forces a definitive output of 1. These logic operations prove classical gates naturally accommodate unknown variables, as long as at least one input provides enough definitive weight to force mathematical closure. This introduces a meta problem. How does a system process inputs when the operation is undecided between AND or OR gates? The unknown gate acts as a piecewise filter, processing inputs through and OR logic simultaneously. If both interpretations yield the same definitive 0 or 1, it outputs that value. If they conflict, the gate refuses to guess, outputting an unresolved state 2. This structure ensures the output remains open unless a conclusion is inevitable under every possible interpretation. The gate avoids producing a definitive state when the underlying logic is in conflict. This leads to the central architectural unification, the single interpretation gate, M, taking inputs A, B, and context parameter G. Setting G to 0 forces AND behavior. Setting G to 1 forces OR behavior. The mechanism is elegant. When context G is set to a definitive 0 or 1, the logic operates as a simple majority vote. For example, if inputs are 0 and 1 and G is 1, the 1s mathematically outweigh the 0, tipping the output to 1. In an AND scenario, input A is 0 and B is 1, but context G shifts to 0. The two zeros now hold the majority, outweighing the 1 and tilting the output to 0. When context G is entirely unknown, set to an open state 2, the scale loses its bias. It rests in balance, only tipping to a conclusion if inputs A and B perfectly match each other. Proving that and or are merely biased contexts of a single median operation dismantles traditional hardware logic. It allows engineers to build dynamic, self-interpreting logic networks that adjust their own rules based on surrounding data. Applying this architectural logic to living, self-configuring systems requires understanding the dual behavioral nature of State 2. As an input condition, State 2 signifies a temporal delay. It means the raw incoming data simply has not resolved into a factual state yet. As an output condition, the meaning changes entirely. It signifies that an internal systemic conclusion cannot honestly be closed based on the facts currently available. This dual functionality allows State 2 to act as a structural placeholder for missing reality on the front end, while acting as a mathematical guarantee of computational honesty on the back end. This diagram shows binary logic's standard assumption. An unknown state sits halfway between true and false on a horizontal continuum. Ternary ambiguity rejects this. State 2 sits on an orthogonal vertical axis, totally removed from the continuous line between 0 and 1. Generating an output of 2 signals that the observed phenomenon physically cannot be contained within the system's current binary decision space. For modern architectures like semantic blockchains or dynamic AI neural networks, forcing a quick decision is actively harmful. Preventing absolute data collapse is the priority. A mathematically rigorous intelligence requires the architectural capacity to state unknown. It must carefully hold the logic open until it has actually earned the right to close the truth.